Okay, well, it's very good to be here. It's an impressive group of people, and it's very good to be discussing the philosophy of cosmology. And I want to talk about cosmology and the limits to science, and I'm talking about cosmology with a big C and a small c, which I will explain as I go on. Now, the basic enterprise of cosmology to use evidence-tested theory to understand major aspects of the universe in which we live. And the foundational issue, which has been realized for a long time, is the uniqueness of the universe. There's only one universe. So we have to extrapolate from aspects of the universe to hypotheses about the seen and unseen universe as a whole. And because there's one universe, standard methods of theory testing rely on comparing similar objects to determine regularities. We cannot use those methods when you've only got one universe. You can't compare the universe with any other universes. That's the basic problem, and that's why philosophical issues must arise and be inevitable in looking at cosmology. Now, the nature of any proposed cosmological theory is characterized by a set of features which each raise philosophical issues. And the answer may be obvious or taken for granted by the scientists in many cases, and so seem hardly worth mentioning. However, cosmology cannot be done without engaging philosophical issues, particularly because it's pushing science to the limits. And making these philosophical issues explicit clarifies what's being done and raises issues that needs attention. And as I've said elsewhere, if you do not look at these issues, it doesn't make them go away. The philosophy is still there. It is simply unexamined, and it's better to examine your foundations than to have them unexamined. Now, I'm going to suggest a framework for looking at this, 7 features. Firstly, what are the scope and the goals of the theory? Secondly, the nature of the theory. What kinds of causality and explanation do you think of? Third feature, what are the priors of theory, the range of alternatives which you set at the outset and therefore shape what you do with the theory? Fourth, what data do you use for the theory, what's measured? 5, what are the outcomes of the theory? What is claimed to be established or explained? 6, the limits to these testing of outcomes. And then 7, bringing it together, what's the relation between theory, data, and the limits to science in the context of cosmology? Now, the scope and the goals of the theory. I define cosmology with a small c as dealing with physical cosmology and related mathematical and physical issues. Defining and testing of mathematical physics theories for the physical universe on large scales and so on. And many of the talks here, such as the previous one, are cosmology in this sense, mathematics, physics, what they say about the universe and its large-scale structure. And that, of course, is a fantastic subject of investigation, which we're going to hear a lot about. It's a purely scientific exercise. However, because of the exceptional nature of cosmology, which I just mentioned, there's just one universe, it pushes science to the limits, particularly when considering what can be said scientifically about the origins of the universe or the existence of a multiverse. Those are the 2 places where we will particularly find philosophical issues coming to the fore. By contrast, cosmology with a capital C is the way it is referred to by anthropologists and sociologists and so on. In addition, it takes all of that seriously, but in addition, it tries to deal in one way or another with the major themes of existence, meaning, and purpose that are raised by the physical universe being the context for our existence. So we exist in the physical universe, but we experience meaning in our lives of all sorts of kinds. For instance, we wouldn't be at this meeting if we didn't think it was meaningful to be at this meeting. How do these issues of meaning and purpose relate to the physical universe? That's cosmology with the capital C. So cosmology with a capital C tries to relate to issues of meaning, purpose, and whatever in some kind of way, in a way compatible with what we know about cosmology with a small c and physics. Now, so this issue of cosmology with a capital C raises many themes in philosophy and metaphysics. It has to propose how one make some kind of stand on these metaphysical, philosophical issues. even though this is highly controversial territory. And of course, I will claim very strongly this territory cannot be explored by science. This takes you outside the domain of science. That doesn't mean it's nonsense. It has its own standards of rigor, its own standards of evidence, its own standard of discussion, but it's not a scientific domain. The major point to make here is that philosophy or cosmology discussions need to make clear which topic they're dealing with. When we do philosophy of cosmology or when we do cosmological theories, which are we doing? Are we doing cosmology with the small c or the large c? Now, either is a legitimate topic for investigation, and you can choose which you want to tackle. But what is not all right is to use only the methods of the first and claim to solve problems of the second. If one wants to tackle cosmology, capital C, one must use adequate methods to do so, involving adequate scopes of inquiry, methods, and data. You may not think that the latter is what cosmology or cosmologists may be dealing with. You may say, why am I bringing this all up? Well, the reason is because some scientists are proclaiming loudly about these issues in highly publicized books and lectures. There are scientists putting out books saying they've solved the problems of the big C cosmology using the methods of the small c cosmology. The drive to consider these issues thus comes from some cosmologists and scientists. It is, of course, of great concern to the public at large. It's one of the reasons we get funding from the public, because they think we're going to provide some evidence about cosmology with the big C by studying cosmology with the small c. So I propose that we can legitimately study either one or the other. If we wanted to study the cosmology with a capital C, we must consider these further issues. We can choose to do so or not, but we must make a clear decision. Which are we doing? And whichever we choose to do, we must use adequate data, theory, and philosophy to handle it. So that's about the scope. Now, the nature of the theory, the kinds of causality and explanation envisaged. And of course, setting up what causality you will look at sets the foundation for what you will do. Now, what kinds of causality are possible in the universe and how do they relate? Physical cosmology has basically got a kind of, as all physics does, two things. Necessity, based in physical laws that are fixed and immutable. They don't change with time and space. They were the same forever in some sense or other. And on the other hand, chance. And chances in the boundary condition, they could have been otherwise. So the point about the physical laws is they couldn't have been otherwise. And the point about the boundary conditions is that they could have been otherwise. So the one is contingent, and the other is in some sense necessary. Okay? So the first issue, which is one of the very deep issues which has been around for a long time, we normally break up science, and Jacques Monod said, into chance and necessity. How does that make sense in the context of cosmology when you can't change the boundary conditions of the universe? So you can't try other boundary conditions. If you can't try other boundary conditions, the difference between boundary conditions and laws becomes blurred. It's often difficult to tell which is which. Because there's only one occurrence of the universe, one specific set of boundary conditions is set. In some sense, that becomes a law for what happens because it can't be varied. Chance, therefore, appears to be necessary. Well, what kind of causal laws hold in the universe and what are their properties? And we have a set of laws that most of us believe in. Variational principles, symmetry principles. We choose specific kinds of variables. We choose their interactions. We have a number of dimensions. These usually lead to PDEs or to path integrals, and we all know all about all of that kind of stuff. With suitable initial conditions, it leads to emergence of higher levels of complexity with effective dynamics and variables at each emergent level. And one of the very important things that happens here is we have our fundamental laws, particle physics. Out of that emerges nuclear physics. Out of that emerges atomic physics. Out of that emerges solid state physics, chemistry, and on the one hand, planetary science and all the rest of it. On the other hand, biology, microbiology, and all of that kind of stuff. And so we get these emergent levels of reality coming out of the underlying stuff. Now, the laws of physics are not by themselves physical entities. A law of physics isn't a physical thing. It is an abstract principle. It doesn't exist as a physical entity. It exists as a principle that controls physical entities. One of the big questions, the foundational issues, does a law of physics prescribe or describe? Does a law of physics make things behave, or does it describe how things behave? Whichever that is, if it's prescriptive, then where or in what sense do the laws of physics live? Is there some abstract Platonic space from which they kind of grab hold on physical reality? How do they get their power? If they are descriptive, then in some sense they are mental rather than out there. But then the question is, why is the behavior of matter out there such that these laws describe them adequately? All the standard stuff which I'm sure you've all thought about. How are they related to mathematics? Why are they mathematical in form? Is the mathematics essential to the laws of physics, or is it just essential to the way that we think about the laws of physics? The deep philosophical issue is why the laws of physics exist and why they have the nature that they have. Now, the point about this again takes you to the philosophical domain. It's why I use the word philosophical there. Physics, like all, takes as its starting point the existence of the laws of physics and then works on and finds out what happens as a result of the existence. But why they exist and why they have that form, you can't do a physical test about that. It's not physics, because you can't do an experiment in which you set up different laws of physics. You can't do an experiment finding out why the laws of physics are what they are. So it's not physics, it is metaphysics. Now, such laws are associated with possibility spaces, and one of the things which I recommend is thinking about possibility spaces rather than laws. A possibility space is a space of possible solutions of the laws. These underlie the theory outcomes and express the nature of the necessity by characterizing what is not possible. And we partly understand the nature of the possibility spaces. They include phase spaces, Hilbert spaces, in quantum theory, the landscape of string theory, M theory, logical possibility spaces. These are possibility spaces, and the thing about a possibility space, in some sense, they are more real than the contingent physical world in which you live. Because when you throw a football or send off a spacecraft or whatever, you cannot violate what is allowed by that possibility space. You can choose your trajectory within the possibility space, but you cannot violate what the possibility space says is and is not possible. Now, these possibility spaces they're another way, in a sense, of expressing the laws of physics, but in some ways I prefer to talk about them for reasons which will become apparent later on. Now, they exist as unchanging, abstract, in my view, Platonic spaces, independent of us and our knowledge of them. Our knowledge of them increases with time. And one mustn't confuse ontology, namely the existence of a possibility space, with epistemology, which is how we describe it. The possibility spaces in which the phase space exists, it describes the possible motions of particles and so on, conservation of momentum, conservation of energy, those all hold in that possibility space, whether we know about it or not. Makes no difference whatever. Our knowledge, however, gradually increases over time, and over the course of a couple of hundred years, we discovered conservation of momentum, conservation of energy. That didn't change the possibility space, it just changed our knowledge of the possibility space. Now, they're hierarchically structured because there are all these different levels I mentioned, multiple layers of description and effective behavior, depending on the level of averaging used, relating to particle physics, atomic physics, physical chemistry, and so on. They're often locally describable terms of suitable mathematical equations, and equations themselves also live in a possibility space. I'll talk about that in just a minute. The dynamics may include attractors and be largely described by constraints. For instance, a lot of the dynamics is described by the constraints in the possibility space, such as the Hamiltonian constraint. So that's a bit about laws of physics, their description by possibility spaces. And then the big issue, in a sense, for cosmology, are there laws for the cosmos as a whole? Is there, you see, you've got this hierarchically structured stuff. Now, what Einstein discovered is you could start with the law at the bottom, the law of gravity as locally applied in the solar system, and apply it everywhere locally, and you get a law which applies to the cosmos as a whole. So there's a bottom-up emergence of a law for the cosmos by locally applying the laws of general relativity everywhere. But from time to time in cosmology, people propose laws for the physics as a whole. That's a law that applies at a completely different level of description. Is there a law for the universe? Now, for instance, is there a law for creation of the universe? That is not a law for creation of particle physics. It's a law for creation of the universe. It's a completely different kind of animal. People used to talk about the cosmological principle as a law that applied to cosmology as a whole, not to the parts, but to the whole. And so one of the questions is, are there laws for the cosmos as a whole? If there are, how do you test them? And of course the answer is you can't test them, again, for the reason which I've already said. There's one universe, you can't compare. So you can make any theory you like about laws for the universe, but you can't test them. Now, the second thing is chance. There's randomness or chance outcomes that occur within the universe due to statistical interaction between levels. When you have these different levels, it's really important that between the levels there's statistical fluctuations at this level which affect what happens at the next level up. And this happens all over the place, for instance, the measurements we were just hearing about. Lower level information is hidden when we use higher level variables, so you average lower level variables, you lose information, and you get your effective laws at higher levels. Now, one of the basic questions, is there determinism in the universe or irreducible randomness? And I take the view, because I believe in standard quantum physics, that irreducible randomness occurs in experimental quantum physics. The initial data does not uniquely determine the outcome. Now, a lot of people try to deny this in various, but I think this experiment is one of the most fundamental things we must take into account. There is nothing physics knows which will predict where those particles will hit the screen. There is therefore, as far as particle physics is concerned, as far as experimental physics is concerned, an irreducible element of randomness in the universe, and it is not true that the universe, what happens in the universe proceeds in a deterministic way. So I think that this is the standard experimental result from quantum physics, and I think we should accept it for what it is, as being something which has been established for over 100 years. Now, there are various ways to show that this does not happen. For instance, the many-world interpretation, the pilot wave theory, and so on. None of them alter what we actually experience in the laboratory as we try to predict the outcomes of specific interactions and events from initial data. So in your laboratory, and you're doing an experiment, it doesn't help to be told there's all this wonderful machinery behind the scenes in which things are deterministic. What you experience in the laboratory, and you test and you verify, is things are not deterministic. And I think we should take that seriously. So that's what happens within the universe. And then the question is, can we use the idea of chance as applying to the universe as a whole? People talk all the time about probabilities of universe models. Is there any sense in talking about the probability of the cosmos as a whole? If so, what's the context within which it makes sense to talk about probability of the universe? Is it a meaningful concept? And if so, how do we cash it out? And of course, the multiverse is an attempt to make a context whereby we can talk about chance in the context of the universe as a whole, not of things in the universe, but of the universe as a whole. Now, what's the relation between the chance and the necessity? Well, this is where the issue of probability measures enters, and the question of how we decide on appropriate probability measures. Now, in ordinary laboratory physics, you can do experiments and you can propose probability measures and you can verify if they are good or bad. In the context of the universe as a whole, if chance has any meaning, that is, we've got some multiverse theory, you have to have some probability measure to use the ideas of probability in the context. You can make all sorts of arguments for your proposed probability measure. Other people will make other. The claim I will make is there's no way you can test a probability measure. You can argue for it philosophically, but the probability measure you choose is a philosophical assumption. It's based on arguments which are good arguments of various kinds, but it's not a physically, scientifically testable thing, that probability measure that you are proposing. This is highly disputed territory. I will make the case that possibility spaces are the best way to describe all of this kind of stuff. And then the deep issue I've already mentioned, why is there any distinction between chance and necessity at all in the context of cosmology? How do we distinguish laws from initial conditions? Because the initial conditions for our bit of the universe are fixed and cannot be changed. And altering the context can in effect change local laws of physics. The classic case of this was Mach's principle, where boundary conditions, inertia is determined by boundary conditions, Olbers paradox, the dark night sky, the second law and the arrow of time that we're going to hear a lot about, in which if the boundary conditions of the universe were different, local physics would be different. The second law of thermodynamics arguably emerges from an initial condition at the start of the universe. We experience it as a law of physics. But if it depends on a boundary condition in the universe, it wasn't a law at all. It was just actually the outcome of a boundary condition. And so this boundary becomes blurred. The landscape of string theory, we've got local physics here, but actually maybe this local physics isn't really the nature of local physics at all. It's just a result of the local conditions. And so this distinction between boundary conditions and laws is blurred in cosmology, and that's one of the things which is really important in discussing the philosophy of cosmology. And then finally, in terms of causality, to what extent do we want to deal with the emergence of complexity? Well, obviously cosmology deals with the emergence of galaxies, stars, large-scale structure, but does cosmology deal with the emergence of life or not? Is that part of cosmology? Now, that's a decision that you have to make. It's your vision of cosmology whether it deals with that or not. If it deals with life, does it deal to how deep does it go into life? Does it just deal with conditions for carbon to exist, or does it deal with conditions for intelligence to exist, or does it deal with conditions for intelligent beings to exist who believe in moral issues and meaning and so on? Which of those do you want to choose, okay? Inter alia, if you want to deal with complexity, you have to decide how far you will go into these issues, purpose, goals, meaning, that are clearly causally effective in the real world. A lot of what happens in the world around us is in fact determined by issues of purpose and meaning. Because, for instance, this complex in which we are having this meeting was designed by someone who had a purpose in mind when they designed it. Purpose is clearly causally effective in the universe in which we live. Now, to what extent will you take that into account in your theory of cosmology? Okay, the priors of theory, the range of alternatives set at the outset. What is presumed to exist at the start before your theory gets going? Now, ontology, what exists? What's the nature of existence of different type of entities? Will you assume geometry exists, matter, fields, laws of physics, mathematics, the constants of nature? Which of these will be given and which of these will emerge? That's kind of big issue. And then the range of alternatives. The possibility spaces specified in theory depend on the range of alternatives. So these are the possibility spaces we're using in our minds. How big are the possibilities we consider in our theory? And these are the priors of that theory. So what range will be considered for chance and for necessity? And the big point here is you can't test alternatives unless you model the alternatives. You can only consider alternatives if you consider alternatives can you see how robust your theory is to variations in these conditions. So what range of physical laws or regularities will you be assumed to hold? What range of necessity? What range of alternative theories of gravity will you consider, for instance? Do we assume physical laws preceded the existence of the universe in causal terms or came into being with the universe? What about mathematics? So in terms of priors, was the laws of physics priors or were they consequences? Are fundamental constants to be taken as priors or determined? So obviously, I'm just saying these are the kinds of issues which come up here. In terms of the initial and boundary conditions, will we consider, for example, small universes, universes we've already seen around since the time of decoupling? I happen to love those small universes because they have many philosophical advantages. They are geometrically possible. There's no physical law which can prevent them. Will our models take them into account or not? Will we consider anisotropic modes, that is, Bianchi modes? Will we consider inhomogeneous models, the LTB models and Wheeler models and so on? Will we consider multiverse models with different expanding domains? One of the paradoxes of inflation is its claim to solve problems of inhomogeneity and anisotropy. 99% of the inflationary models considered are based in Robertson-Walker models. They don't consider inhomogeneity and anisotropy, and yet they claim to solve problems of anisotropy and inhomogeneity. You can't solve those problems unless you make models in which you've got inhomogeneity and anisotropy. So what pre-exists the universe in a causal sense, in an ontological sense, and this is, of course, a current debate with some acerbity. What is nothing? Can nothing exist? Can nothing cause anything to come into existence? This is entire debate. Books are written about this, papers written. And in fact, you obviously need some foundation to proceed, some basis for chance and necessity. If you have absolutely nothing, you haven't got anything to start with to create a universe. I claim you need possible existence of various Platonic spaces or entities. Now, for instance, if you're going to claim that that the universe is created by the laws of physics, you're assuming the existence in some Platonic sense of all of that stuff, quantum field theory, variational principles, groups, SU10, SO9, whatever they are, Noether's theorem, all of that stuff somehow pre-exceeds the universe if the laws of physics bring the universe into existence. Those are based in mathematics, so in some sense mathematics must also pre-exist the universe. And one of the things I strongly believe in is the Platonic space of mathematics. Math better exists in some real sense, not in our minds, but in our real sense. So I view mathematics as a case of Platonic world of mathematical abstractions being learnt about by the human mind underlying physics and science. Major part of mathematics are discovered rather than being invented. For instance, the Greeks did not want to prove that the square root of 2 was irrational. They found that to their dismay. Okay? And that's a universal truth, true everywhere. It's a Platonic truth. It is true whether human minds exist or not. It was true at the beginning of the universe. It will be true when we've all died out. So this is an abstract rather than embodied reality, independent of the existence and culture of human beings and presumably even of the universe itself. Chunjo and Cons write about that, and Roger Penrose. So these geometrical relations are true everywhere in the universe, which is, of course, why we use them as proposed basis for talking to interstellar beings. And the Mandelbrot set was waiting 14 billion years to be discovered. Nobody predicted it. We couldn't discover it until we had computers powerful enough to produce the Mandelbrot set. It was sitting there hidden, waiting in a Platonic space, wanting to be recognized. Well, all right, I'll withdraw that wanting. Okay, the priors of the theory must be sufficient to support the theory. If it claims to deal with how the universe came into existence, it must include adequate priors to deal with this proposition. What existed previously, in as far as that makes sense, and in what way did they exist before there was a physical universe? You must come up with some plausible statements about that. And of course, these are philosophical, not physical statements. If it has to do with existence of life and intelligence, it must include priors relevant in those areas too. In particular, it must consider the relevant possibility spaces, which I will mention at the end. Okay, data for the theory. What is observed or measured? So what data has been used to test and so legitimize the theory? Well, microscopes, laboratory experiments, particle colliders, telescopes at all wavelengths. We've just been hearing about that, gravitational wave detectors. We use apparatus, which gives us reliable, repeatable, quantitative data for physical and astronomical entities. And this is what has led to the rise of science, a fantastic achievement. And these kind of diagrams, we've seen some, we're going to see more. That's what comes from this data. Now, the data relates to what kinds of issues one will investigate and what variables one has chosen. It comes back to what is the scope of your theory. The data to use to test the theory must be adequate to support its scope. And I want just to say this relates to particular cosmology with a capital C. I'm not going to spend time on cosmology with a capital C. I'm just putting in some markers about this. If you want to deal with cosmology with a capital C, you want to make some statements about how physics and all the rest relates to meaning and purpose. That cannot be adequately investigated on the basis only of physical data. If you want to adequately discuss the issue of cosmology, you must take into account data related to meaning. Please don't come to me with a book where you produce a theory how you've solved the existence of the universe. You've solved all those philosophical problems that philosophers are worried about for thousands of years purely on the basis of physics. If you've done so, your data has excluded all the data to do with meaning and purpose. It's excluded data, Shakespeare, Aristotle, Kierkegaard, Tolstoy, all the rest of them. It has excluded all of the data about what is happening today in Iraq and the West Bank and in Gaza and all of that. If you exclude all of that data, of course, you will come up with a theory which says there is no meaning in the universe. You will have excluded it from the start because you never took the relevant data into account. So I'm not going to take this any further here. I'm just saying to you, if you want to talk about cosmology, please take into account data related to purpose and meaning, as well as data related to telescopes, particle colliders, and the rest. Okay, the outcomes. The outcomes of the theory include models of what is, claims about what causes of their existence are, claims about having tested these statements, claims of unifications of previously separated domains and results. And the first outcome is the expanding universe model with inflation followed by gravitational attraction, providing a physical model for emergence of large-scale structures. The second outcome is unifications of physics and cosmology. Gravitation, atomic physics, nuclear physics, possibly particle physics. So there's unifications. One of the things which I just want to comment on is the big move in the history of cosmology was bringing in atomic physics with the gravitational physics, the dynamics of the universe, atomic physics with the microwave background, nuclear physics with nuclear synthesis. Has particle physics being embodied into the expansion of the universe? And I would say if and only if the Higgs is the inflaton. All of the other proposals for inflation are not related to real tested particle physics. The one which is the Higgs. And so I think that the unification which was hoped for from inflation between particle physics and cosmology will be realized if and only if we can find some way of making the Higgs or some other particle detectable in a collider the inflaton. Yeah. Okay. Right. So this is the standard model. I'm not going to go through that. Okay. We've been claimed multiple levels of multiverses, domains beyond the visual horizon, chaotic inflation multiverses, partially tipped by Planck and Bicep, anthropic multiverses, chaotic inflation with different physics or constant of physics in each bubble, and the Everett many branches of the wave function. These are all proposed sometimes together. In the latter case, every time any single measurement event takes place, there is a bifurcation of the entire multiverse, which I find very difficult to make sense on. But anyhow, these have been provided. And then we've had claimed a universe created from nothing in a variety of versions, cyclic universes, eternally existing universes, and so on. And I just want to make one comment here that eternal existence is in philosophical terms just as difficult as creation out of nothing. If you take eternal existence seriously, it leads to eternal return problems. And philosophically, if you're worrying about what's a philosophically preferable model, that's quite problematic. The limits to the testing of the outcomes. There's limits. Will the theory be tightly constrained by the data or rather largely shaped by the priors assumed? There are major limits as regards the relevant cosmological domains due to visual horizons for all radiation. There are major limits on testing the physics due to energy limits of particle colliders, which limit our ability to test the relevant physics. And so the start of the universe, can we scientifically test proposal for creation of the universe out of nothing or out of something? And I claim no, because we can't do the tests within the universe of the high enough energies, and we can't in any way test what happened or what might have been going on in some sense or other before the universe existed. How do we test if laws based in space-time features somehow had an existence before space or time had come into being? So can these claims about start of the universe be constrained? Well, some outcomes can be, but I think I've said enough about that. You've got to give a framework in which that makes sense, and I don't think that's testable. The existence of a variety of multiverses, particularly the anthropic version. You have to have bubbles, which can be tested to some extent by Bicep and Planck. You have to have string theory true, and that's looking bad because we haven't seen supersymmetry. You have to have a relation between the bubbles and string theory. You've got to have a mechanism for realizing the string theory's vacua. And of course, if you're going to have an Everettian thing as well, you need some kind of way of testing the branching of the wave function if you're going to say that is a part of science. The observable universe domain, that's what we can see in conformal coordinates. The multiverse is trying to make claims about way beyond there on a better scale out there. Everything we can see is in that little triangle in a Penrose diagram. We're claiming to tell you what happens way out there, and the word infinity is often used. And this is a great bit of hubris to say from what's happening in there, we can say what's happening way out there. Is the multiverse implied by known physics? No, it's implied by an extrapolation of known physics way beyond where that physics is tested into new domains, and that extrapolation may or may not be correct. There is this talk about bubbles, colliding bubbles. I would find that quite convincing if we could find circles in the sky where the fine structure constant was different from other ones, because then you would be seeing a bubble where physics was different. And Jean-Philippe Houzin, for instance, has written about that. But will the multiverse enthusiasts drop the multiverse claims if we don't see this? No, they won't, because there are billions of other multiverses out there, and only in some will that be seen. And I really want to protest the often claimed existence of physically existing infinities. Will infinities occur in the theory? If so, will they play an essential role? And I believe that any theory which relies crucially in an essential way on infinities is a faulty theory, because infinities cannot exist in physical reality, because no matter how far you go, no matter how much you do, an infinity is always beyond what can be obtained or what can be seen. And Hilbert said this: the infinity is nowhere to be found in reality, no matter what experiences, observations, and knowledge are appealed to. So I think all of that stuff which relies on infinities is not science, it's some kind of philosophy. And particularly because you cannot test any claimed existence of infinity by observation or experiment. It's a huge hubris to extrapolate from one small domain to infinity, never encountering a limited. And so I don't believe in any theory which relies on infinities in an essential manner. Okay, so finally, theory, data, and the limits of science. The very nature of the scientific enterprise is at stake in the string theory and the multiverse debates. Proponents are proposing weakening the nature of scientific proof in order to claim that multiverses, together with string theory, provide a scientific explanation. Leonard Susskind has explicitly stated that. Richard Darvid has done that in his book String Theory and the Scientific Method. And Sean Carroll has done that. And it's very, very good that Sean and these others have brought it out into the open, because this is a key debate. Should we continue to say our theories are scientific if we can't test them in the usual scientific manner? And if so, in what way? And I think this is a place where the philosophers and the cosmologists and the physicists should be getting together and talking about it. I think if you weaken what is called a scientific theory, it's a dangerous thing to do. And I think if you're not very careful, you will find you have admitted all sorts of things into the tent of science you didn't want to be there, like, for instance, intelligence design and astrology. The criteria are satisfactory structure, intrinsic explanatory power, extrinsic explanatory power, observational and experimental support. Everybody's theories have 1, 2, and 3. The scientific one, the key one, is the last one. And so I think it's particularly the last one, the observational evidential support. The two central scientific virtues are testability and explanatory power. In the cosmological context, they're in conflict with each other. The extreme case is the multiverse, where no direct observational test of the hypothesis are possible. As the supposed other universes cannot be seen by any observations whatever, the assumed underlying physics is untested and probably untestable. In this context, one must reevaluate what the core of science is. Can one maintain one has genuine scientific theory when direct and indeed indirect tests are impossible? And it's been proposed that the real reason we should do this is because of the vacuum, the cosmological constant. I'm just going to say trace-free gravity will in principle sort that out, the unimodular gravity. But in any case, supposing you've got the multiverse, it doesn't solve any of the fundamental problems about the nature of existence. You've got a multiverse. You've still got to ask the same questions. Why does the multiverse exist? Why do its laws exist? Why do they have the form they have? Why do they have the constants they have? Why is the multiverse a solution for life? So assuming a multiverse does not solve any of the fundamental philosophical issues, it just puts them back one stage. And as regards cosmology with the capital C, and this is my closing remarks, I've already emphasized these possibility spaces. Now, when you get to cosmology with the capital C, there's a series of really important possibility spaces for physical existence, but also for mental existence. There's possibility spaces for biological existence, which the biologists call the landscape. There's possibility space for thoughts. We can only think thoughts if thoughts are possible. What thoughts were possible was, in some sense, determined before the universe began. You can't think thoughts unless they lie in a space of possible thoughts. In particular, there are a possibility space for values. What is good and what is bad? Now, you may or may not agree about what those are, but at least the possibility of thinking about what is good and what is bad exists, because a possibility space for such thoughts exists, and in some sense, like the possibility space of mathematics, exists through the universe and has existed forever. So the coming into existence of things that make these possibilities real is the second stage, but the deep issue is, why does the possibility spaces exist? So I think I've used up my time. I will just go back to my summary there and say that I think the really deep issues, there are possibility spaces for physics, for mathematics, but also for those things to do with what make us really human. If you want to deal with cosmology with a capital C, you must relate to the latter. If you want to do with cosmology with a small c, you will only relate to the former. But I think possibility spaces is the way to go.
Okay, let the fight begin. Jim?
George, I think from listening to your talk, I've been doing cosmology with a very small c all these years. But if I understood you correctly, in order to promote myself to a higher level of something, that I should deal with a meaning and purpose.
Yeah.
Can you say what you mean by meaning and what you mean by purpose?
What I would like to focus on is meaning and purpose is what history is about, it's what literature is about, it's what a lot of philosophy is about, it's what drives people to do some things and not to do other things. I think the one I would focus on most is the ethical kind of issue, and I've already mentioned the ones which I think is the core for people today. This varies with epoch in the history of humanity, but the core today, does it matter what's going on in Iraq and in Syria and in Gaza and so on? Okay, now, as physicists, we have nothing to say about this. As human beings, because physicists are human beings, we have something to say. But the point about it is, as physicists, we have nothing to say either one way or the other. Physics has nothing to say about any of those issues. So meaning is to do inter alia with what is good and what is bad, what is right, is wrong, how we should behave, what we should do next, and that kind of issue.
Thank you, I guess.
Simon.
Well, no, I'll speak loudly. George, my worry is that you're reinventing the wheel. So much of what you call cosmology with a big C is already dealt with in whole swathes of not just philosophy, but many disciplines. And also my worry is that cosmology with a small c, I'm not sure if that really hits the mark either, partly because you didn't say so much about it. But here's just a kind of a game to play, really. Go through every one of your slides and ask yourself the following question. To what extent could one ask the same question of biology and the history of life on Earth?
Yeah.
Well, you say that happily, but isn't there something a little mistaken about, insofar as we're doing something at this conference, we're trying to say something about what is philosophy of cosmology. It's a distinctive discipline. To sort of put into it every single other discipline one can think of surely is not helpful. And in particular, to put in other disciplines in science, such as biology, it seems just a mistake.
So my problem is, as I said at the beginning, it's up to you which you want to do. And if you want to say cosmology with a capital C, it's been done by thousands of other people. Yes, I agree. What hasn't been done adequately is the relation between that and the physical cosmology, the relation between the capital C stuff and the small c. Let me just give you a very specific example of that. The Oscar Pistorius trial has just taken place in my country. Jerry Coyne has just put up on a blog that Oscar Pistorius was not responsible for what he did because physics determined what he did, and therefore he shouldn't be put into jail. Now that's an example of how the views of physicists are being used, of how a view about how physics works and relates to complexity is supposed to relate to everyday life. That's one kind of thing. The next kind of thing is that the books, for instance, by Lawrence Krauss, coming out saying now he's now proved the existence of the universe out of nothing, and therefore he has proved that the existence of God is irrelevant, and therefore all those millions of Muslim people, Jewish people, devoted Christian people are wasting their lives doing what they are doing. Yes? Now, this is now how people are trying to relate the small c and the big C. Now, I happen to think that Lawrence Krauss has no justification for what he claims about this, but whether you think that or not, what I'm telling you is that some cosmologists are making claims which have implications for humanity and how humanity see themselves. The world of astronomy now is becoming more and more international. I deal with Muslims. I've just been working with a very devout Muslim on a project to do with black holes. And there's no way that he can relate to what someone like Lawrence Krauss is saying. And Lawrence Krauss is trying to claim this is a scientific conclusion which follows from studying the origin of the universe.
Yeah, George, I like your talk very much. I was almost agreeing with everything you said, but there's one point on which I try here to largely to disagree very much. That's when you're saying that mathematics pre-exists the universe. I remember a remark by Murray Gell-Mann, who was telling us that mathematics is really physics. We have just forgotten it. So it's a language which is developed within the physical, the universe in which we are built. It's very strongly tied in with the universe and the structure in which we inhabit. So, I mean, this that the mathematics as a language is completely independent of the physical nature, and I mean, it's a refined version of our language, which is also developed in very, very strong tide with the way the physical universe is constructed. So I strongly disagree with that viewpoint of yours, this Platonic view of mathematics. I don't think it's very easy for you to argue for that, actually. There was another point. I mean, you were speaking about...
Can I respond to that first? But one must be very, very clear, as I said, between ontology and epistemology. We discover there was a period in human history when we didn't know the square root of 2 was irrational, and then there was a period when we did. The fact the square root of 2 was irrational was unaffected by what we knew about it or did not know about it. And so one must really... And so what I'm claiming is that fact was there all along, always will be, and always has been true. Supposing we all die out and the knowledge that the square root of 2 is irrational dies away, the square root of 2 will still be irrational. And it's in that sense that I believe it's a Platonic fact.
I was given the microphone, so you're not going to get to make your second point, sorry. So I've always been confused about this issue of boundary conditions. So if I look at a very simple system, I push a marble off a hill and I say, well, I just use laws of physics, but the boundary condition is this initial condition, as though it's separate from the laws of physics. But of course it's not really. I know that there's an interaction with my hand and the marble, and that really it's part of the laws of physics.
Yeah.
So what I'm confused about is in the early universe, is that the only example where we can really separate boundary conditions from laws, or are we mistaken for trying to approach it that way? Should we be thinking, its boundary conditions as somehow being predicted or part of the laws of physics?
I'm not quite sure how to answer that one. In everyday life, what you do in a physics experiment The Copenhagen interpretation actually applies to classical physics as well as to quantum physics. You, the experimenter, set the thing up, and you don't describe that in your physics experiment. And then you start your physics, you turn physics on, as it were, at the moment when you have finished setting the experiment up, and you then does its thing, and you then take your readings. You taking the readings outside what is described by the Copenhagen interpretation actually applies to classical physics as well. And so you could say, shouldn't you step back and ask, how did you get to place the ball at the top of the hill? And then you end up with a whole bigger scheme of explanation and so on. And if you keep following back, you get back to the universe as a whole. For practical purposes, what physics assumes, the practice of physics assumes we have free will. The practice of physics assumes we can make a theory, we can set up an experiment, and we can press the start button and it will then get going. It is based on the assumption we have the free will to think of the theory, to devise the experiment, to set up the apparatus, and to press the start button. And that is all outside what the physics describes. It's the preconditions for physics to be a viable subject.
Yeah, George, I agree with a lot of what you said about multiverse theories, but I think you were a little bit too strong about the testability. So, for example, for many years, I've been arguing within the context of the landscape of string theory that the assumptions of the theory itself make predictions about what we should expect the values of a variety of constants in corrections to the standard model should look like, and that those predictions are just clearly wrong, experimentally wrong. So, for example, there's a prediction that you would get without further knowledge, mathematical knowledge of the landscape of string theory, that the only thing that bounds the baryon number violating interactions should be the fact that at a certain level they would prevent our existence. And that's just wrong by many orders of magnitude. And there are 10 fundamental constants in corrections to the standard model, more than that, which are similarly predicted by this kind of completely random theory to have values that just are not compatible with experiments. So there is a certain extent to which you can test multiverse theories if they make very specific predictions about the values of things.
Just one comment. That's the multiverse theory has got various components. That's one of the components of the multiverse theory. I'm very interested to hear what you say. I thought people were still searching for a vacuum which would give you the standard model, and you're telling me it's not possible, which I would find very interesting.
What I'm saying is that given that you've got the standard model, there are a variety of corrections, higher dimension operators, that have no reason not to be there within the standard model. In theories where you don't have random determination of coupling constants, you can say there's some symmetry that prevents these operators from being there at some level, and that's compatible with experiment. But if you say the only reason that these parameters have the values that they have is just their random numbers compatible with the existence of us and so on, you just predict things that are incompatible.
People are begging for coffee. So I'm going to take two quick questions, one from here and one from Billy.
This is a simple question. I may have misunderstood what you meant, but you said that any theory that relies on infinities in some way or another is doubtful and shouldn't be considered seriously. So would that rule out any theory that relies on the use of the real numbers?
Yes, it would, and in the sense that I believe strongly from this basis that it suggests that space-time is quantized. In that case, at the basis of physical laws is a discrete space, something like that causal set theory has, and the apparent continuum is only apparent, it's not actually a continuum. In other words, I do not believe it is physically at all plausible that between my fingers there is an uncountable infinity of physically distinct points. I don't think that even makes sense. But if it makes sense logically, it's not a scientific statement. There is no experiment you can do that will ever prove that to be true. So if you want to claim that, it's philosophy, it is not science, if science relates to testability.
couple of comments. One was your discussion of laws of physics and your inability to change those laws of physics, and conclusions that you drew from that. One of the wonderful things that we've discovered about physics in the 20th century is how huge numbers of systems behave in a way in which they seem to be obeying the same kinds of laws of physics in all of these cases. I mean, the whole field of analogies and so forth that I've sort of played with black holes and so forth. And there you have an opportunity to, in fact, test what happens when you change the laws of physics, because while I can't change gravity, let us say, around a black hole, I can't change Einstein's theory, I can, by using the analogy with, let's say, water flow, change various aspects about that flow of water, which will change then the behavior of quantum fields, et cetera, in the vicinity, and ask questions about what happens when I make those changes.
Could you do such a theory about creation of the universe? Could you make an analog model of creation of the universe?
I could, yeah. I mean, there is the possibility that I could do that as well. If I have a theory about the creation of the universe, let us say general relativity, I can then find perhaps, I mean, I don't claim to have one in my back pocket, but I could find a system which behaved in a similar way, but one in which I had more control over the various interactions within the system and actually make changes in that to see how this new system would behave in a similar situation. So one has that kind of a possibility, I think.
But you have to worry about whether the analog continues to be true once you...
Of course, but I'm just saying that one does have the possibility of changing laws of physics by using these kinds of analogs. In many ways, that's a real surprise. I mean, it's something that the 20th century has showed us, is how uniform the world is, that, you know, things in the cup of water can behave in many ways like things way out there in astronomy, that they're described by exactly the same kind of mathematics. And I guess my second comment I better cut off because I'm being told I have no more time.
Shall we thank our speakers?